Swayam Prabha. Digital India. Educated India.
So let's say you have two surfaces to be matched, x and y. Okay, we need to define the distance between these two surfaces, and this distance is the shape distance. Okay, so therefore, this distance must be invariant to any rigid transformation. In fact, this should be invariant to, used the wrong term, it should be invariant to any similarity transformation. Okay. And for now, if we assume that both the shapes have n vertices, this is something you have seen earlier in Professor Suesh's presentation. Without doing anything to x and y, if I just compute xi, the distance between the ith vertices of x and y, and add it over all vertices, it also gives me a distance, but of course, this is not a shape distance, right? Is that okay? And that's not going to give you a shape distance, right? Because if I shift the surface x, translate it, this distance may increase. Okay, so this doesn't make sense, right? Because it's not, of course, invariant to rigid motion or similarity transmission. Once again, typo there. So, how does one eliminate rigid motion? That's the question, and the added complication is here. The added complication is correspondence information is missing. Right? So what do? You have two problems, right? Correspondence and rigid motion. You can see that both these problems are sort of interrelated in the sense that if correspondence is available, then there is no issue. I can go ahead and find the optimal rigid transformation that aligns the two. Okay. How? Align the centroids. Second, find the optimal rotation the way I described in the first slide. Secondly, if I know the best rigid transformation or best similarity transformation that aligns these two objects, then I can find a correspondence, isn't it? How? If I give you the best similarity transformation that aligns these two objects, how will I find the correspondence then? Anyone? So if I give you the best similarity transformation that aligns these two, I would apply that particular similarity transformation to the object, right? Okay, Sanchi has an answer using centroids. Can you be more specific? I'm telling you that I'm giving you what is the best rotation you have to apply and best translation to apply so that the two align. Right? So finding that is not an issue. Once I give you that, how will you find the correspondence that this vertex in shape 1 or object 1 corresponds to this vertex in shape 2, and so on and so forth for all vertices? How would you do that? Sachi, if you have an answer, please go ahead. Okay, Darshil says we will apply that transformation, okay, and then do what? Maybe you can speak up, Darshil, if typing takes a long time.
So we will apply the transformation and then the closest point we get, that is our
Corresponding point.
correspondence point. Yes.
Right, because I've aligned the two shapes now, right, to the best possible arrangement. Align means now you will have points which are close to corresponding points in the other shape. So all I have to do is, after aligning it, take every point, find which is the closest point in the other shape, and by closest I mean according to the Euclidean distance. Okay, so find the closest point in the second object. That would be the best estimate, right, of the corresponding point for this particular vertex. Repeat this for every vertex and you will have a point-wise correspondence available to you. Okay. Now the issue is, of course, both are unknown to begin with, right? If one is known, the other can be found, as we just discussed, but unfortunately both are unknown. So what do you do? This is again an optimization problem. I hope you see that. And a particular strategy which is very popular is what is called an alternative minimization. Insert a slide here just to write this down. A slide more. Just a minute. So let me sort of represent correspondence by a vector C. Right? Ci equals j if vertex I corresponds to vertex j. Okay, I hope the notation is clear. Then you have then propose a cost function which is a function of two variables. One is the set of optimal transformations. So let's for now ignore scale, right? So that I won't be wrong whenever I sort of say rigid transformation. These are one set of variables. The other is, what is this correspondence? What's the best correspondence? Okay, and we sort of put it in this way: I equals 1 to n r xi plus t minus y of, even can you finish this? What is the y corresponding to xi? Oh, sorry, vi. It should be consistent. Patience, sorry for that. Vi plus t minus y of, sorry, again this should be w. W of what? Even what would be the corresponding vertex to vi given this C? Clearly see here, it should be C of I. Right? C of I gives me the index of the vertex in the second shape, and the vertex is given by W of that index. Hope this makes sense. Yes. Right, so you can see that there are these two pairs of variables that we want to optimize. How do we do that? This is what is called alternative minimization. The idea is, you basically, okay, Vignesh has a question. How will we deal with the additional freedom? So what freedom are you talking about? So C is not freedom, right? It's encoding another variable that you want to optimize. The number of equations is the same. It's not really. So how many equations are there, right? N, right? Or I mean, you're adding this up, isn't it? And how many variables? 7 here and n here. Okay, so are you talking about unique solution or something like that? I mean, you're not trying to solve an equation, right? You're just trying to optimize this. You want to minimize this cost function. So I don't know if I've answered your question, Vignesh. Let me continue. So what I'll do is I'll first assume T0. Okay. Once I sort of assume C0, let me sort of assume this is the right correspondence. Then what do I do? So since this is sort of having faith, maybe, I don't know if that's the right way to put it. So given this correspondence, I can now go ahead and compute what is the best rigid transformation that aligns as per this assumed correspondence, right? That is not difficult. Next, you apply this optimal transformations to your object 1 and then see, do you need to rework this correspondence? In other words, obtain a new correspondence. From this new correspondence, again obtain the best rigid transformation parameters and continue doing that till, of course, there is convergence. Okay, by convergence I mean maybe these correspondences and these optimal rigid transformation parameters are not changing much. Okay, in that case you stop. Okay, and in some sense that's the best we can do, right? I mean, we don't have anything to begin with. We can only make some assumptions and then try to improve on those assumptions. So that's the idea. And you can see why this process is called alternative minimization. You sort of assume one is given, optimize for the second. Once you have hopefully a better estimate of the optimal second parameters, you try to improve on the estimate of the first set of parameters. Okay, I hope the overall picture is clear. And by the way, this is something that you're supposed to code in today afternoon session. Okay, with of course there is help from my side available, and I think you should be able to do this. Okay, so let's proceed with this. This particular algorithm is what is called the famous, it's a very popular and of course an old algorithm called the ICP algorithm, standing for iterative closest point algorithm. Okay, so yeah, that's the idea I've just described. Let me just discuss this in detail. So as I said here, as I've written here, you assume some initial correspondence. How do we get this initial correspondence? So the idea is given, so again I've used a different notation here. This should be Vi, this should be Wj. So given a vertex, ith vertex of your mesh X, to which point in the mesh Y does it correspond to? Right? What you do is you basically find the Euclidean distance, right, of this particular point. Okay, I think maybe I've done it the other way around. Okay, so in the mesh Y, right, I want to find out to which point does the vertex yj correspond to in the mesh X. Okay, so what we do is you basically compute the Euclidean distance of all points xk in the mesh X to this particular point yj. Then you of course take the point in the mesh X, which is the closest. That is your corresponding point. And you of course do this for all points yj's. Okay, so that's going to give you your initial correspondence. Once you have the initial correspondence, you solve this optimization problem, and that yeah, you have seen this optimization problem at least in 2 sessions, I think. Yesterday's session we solved this problem, and in a 2D version we solved this on last Tuesday in Suyash's session. Okay, so by now I hope you are familiar with this, not of course all details, but at least from an overall perspective you, I hope, are aware of this. Okay, so yeah, estimate the rigid motion. Translation, just align the centroids, right, as expected, and rotation using the SVD process. Find the covariance matrix of the centered meshes. Okay, that's going to give you your optimal rotation. Apply that rotation to the mesh and then go back to estimating correspondence. Okay, iterate till you have convergence. Let me show you an example of this process. I'm going to use this partial matching problem to demonstrate this. Where do I hope details are visible? So what you see is this is the original red teapot mesh, right? And I've taken a part of it and I've sort of moved it myself. And now the problem is I want to be able to match this part of the mesh with the entire mesh. Okay, so in some sense, I'm sort of simulating a partial shape matching problem. Is the mesh visible, everyone? Okay, and I'm just applying this iterative closest point algorithm to this mesh here. Okay, and okay, so since it's an iterative process, I'm also showing you some of the intermediate steps here. So you can clearly see there is this black point clouds. That is, I think, after a couple of iterations. Right? So you can see, since I'm applying this optimal rigid transformation that I am estimating to these blue points, you can see that it's sort of taking it closer and closer to the uh, entire point cloud or the original point cloud. And then after about 10 iterations, you can see that it's basically coinciding with the whole mesh. As far as I remember, I've not sort of just taken a part of this mesh and put it over here. I've also added noise to it, just so as to simulate a more realistic scenario. It does pretty well, at least in this example. Okay, but there are several issues here. Can anyone of you think of an issue here with this algorithm? It's not very complicated. It has nothing to do with math. What does this algorithm crucially depend on? To match to a similar site which is not really at the right position. And why does that happen, Vignesh? Why can that happen? really see, I mean, if I sort of think of this step as the basis of my entire algorithm, right? Because once this is there, then the rest follows. But so the foundation of the algorithm is based on an assumption, right? So what happens if this itself goes wrong? If my initial correspondence, right, and you can see in the algorithm, what is it based on? How am I estimating the initial correspondence? Just depends on the closeness of points in space, isn't it? Doesn't use any shape related information here to estimate the initial correspondence, right? So if my initial estimate of the correspondence goes wrong, then basically the algorithm will collapse, right? I'll show you an example of that. Okay. Yes, so to handle cattle, but still if you match a spout with any of the spout, that would still be okay. But see what happens here. Right? If my initial, the second mesh that I have to match is somewhere over here, just randomly put on this side, where will my initial points correspond to? Right? All of these points will correspond to maybe points here or here, somewhere here. So it's sort of going in a completely different direction. Then once you are in the wrong valley, right? I mean, again, think of this in terms of an optimization. Yeah, use the red thing. So this kind of a cost function that you're dealing with is certainly not convex. That you may have something like this. If your initial point is somewhere here, right? C0, R0, T0, you're not going to be able to reach this point here, which is sort of, at least in this small example, this is the global optimum. You're always going to get stuck here. Okay, so in fact, mathematically, we can prove that this ICP algorithm, it certainly converges, but only to a local minima. And that should be obvious from this example, right? I mean, if I run more iterations of it, it's not going to move from here. Because most of the mesh does match well with the red mesh. Right? So it is not going to be any movement here. Okay, so it has sort of converged. But of course to a local minima, and of course it's very far from the global optimal solution, right? I hope you can see that. Have I lost some of you? Or not gone into the math at all? I hope you get to see sort of trying to connect the optimization with Suyash's session while discussing these things. So I hope you are following me. So, okay, okay. Thanks for the feedback, because otherwise it's like talking in the dark. Okay, so in the original paper, so this method is very old. It's by Bessel and McKay. The paper is called A Method for Registration of 3D Shapes, published in the IEEE Transactions of Pattern Analysis and Machine Intelligence way back in '92. What they proposed is, so they also knew of this problem. In fact, the paper proves that their algorithm is going to converge, and it will converge to a local minima. So what they said is, in order to avoid this issue, what you can do is you can start with several initial estimates. Okay, so by that I mean, so this is the mesh, right? The initial correspondence process is kept the same, but what they say is you apply thousands of something like that, Vignesh. Not stochastic in nature. What they say is, so how many degrees of freedom are there for R and T? We've just discussed. This problem is in 3D. So this is R3, right? The three Euler angles, just to bring in some concept from yesterday's talk. There are three parameters in order to specify a 3D rotation, and there are three parameters to specify a translation vector in 3D. So this is a six-dimensional space, right? What they say is you sort of take enough samples of this six-dimensional space and apply all these sampled rotation and translation to your mesh that you want to align. And for all those different, so when you apply these R and T to this particular blue mesh, you will get several, the same blue meshes, but transformed. For all those transformed blue meshes, you compute the local minima, and then you compare all these local minimas and try to find for the global minima. Of course, it goes without saying that if you take enough samples of this six-dimensional space, you will end up with a global minima. But I think it, even without knowing the details, I think it should be obvious that it sounds completely impractical, right? It's a six-dimensional space. The number of samples, if you want any decent number of samples here, you would need days and days together to finally finish all the computations, right? So yeah, and in fact, the good thing about their paper is they admit that it is sort of impractical. Yes, so for every different pose that you sample, that other pose may also get stuck in other local minimas. But the idea, or their idea, is if you have enough samples to begin with, then amongst those samples you'll always also find a global optimal. Right? And global optimal you can easily compute, right? All you have to do is to compare this cost function with this cost function and this cost function. So that can be handled. Okay, but just this idea that you will have to take a good enough number of samples of the six-dimensional space, that is very impractical. All right. Okay, so let's look at, so this is sort of the basic algorithm for rigid shape matching, and then there have been several variants of this basic algorithm. Okay, I'm not going to discuss those in details except for one, another very popular variant of this, that's called the sparse iterative closest point algorithm, given by Mark Pauly et al. Quite recently. I mean, I don't know, 2013 can be classified as recent or not, but at least as compared to the original paper, it surely is much more recent. I'll just summarize what is the basic idea. And again, I need to zoom into this so you can see it. No, why is it so complicated to zoom in? Just let me know if you can see this graph clearly. Is the graph slightly visible? Okay, so what this graph is, on the x-axis, you have a single variable z. Okay, on the y-axis you have the absolute z to some power p. Okay, now our original cost function that we were trying to minimize in this rigid ICP process was this, right? So what is this thing in the curly braces? What does it tell you? What is it encoding? What information is it encoding? It is encoding by how much does the transformed point xi not match with yi. Okay, right? So I've estimated an R and T. I've applied that R and T transmission to the point xi. This minus this tells me what is the difference, or basically I can think of this as an error, right? And the cost that we are trying to minimize here, therefore, is the norm of the error squared. Okay, so in this particular plot, you can think of the variable z as the error. Okay, and then you can think of the y-axis as the cost that this error contributes to in our optimization problem. Okay, so this red curve that I hope you can see is nothing but z squared, which is the current cost that we are considering, right? So every point there will be an error associated with it, and that error will contribute a certain cost to the entire cost function, right? So what do you see here, right? So of course, what this means is whether the error is positive or negative, it doesn't matter. It contributes the same amount, and that is how it should be. That's fine. But what do you observe here? So if there are points, let's say my mesh has 100 points. Okay. Out of those 100 points, let's say there are 5 points with, I don't know if you can see this number. This is the number 3. But let's say out of this 100 points, there are 5 points with an error of 3. What will happen to my cost function? Anyone? So compare it with, let's say there are 100 points. Okay, let's take two cases. All 100 points, let's say, have a error of 1. Okay, let's take a second case where 95 points have an error of, let's say, half. 5 points have an error of 3. What will happen? Can somebody compare these two cases for me? And
Most probably, his 5 points may be the noise because of the noise.
no, that's fine. Whatever is the reason behind this, it's a different thing. But what will happen to your cost function? Overall cost function. So by overall, I mean all, you add all these errors together. Error is skewed in the second case. In other words, there will be a higher cost here, right? Right? Because remember, you're doing z squared. So each of these 5 points will contribute roughly with 9 to the cost function. Right? So that's right, 45, right? 9 5s are 45. So only 5 points contribute 45 to the cost, whereas here, right, all 100 points are making an error of 1. In total, the error here would be 100. So 100 points are contributing a cost of 100. Here, 5 points are only contributing roughly half of that already. Okay, so that how you want your cost to be? This is the least square cost function, right? What does least square do? It sort of treats every point equally. So every point is equal for this cost function. And practically, you don't want your error function to behave this way. Why? Because, as Darshil pointed out, maybe your scanner through which you're acquiring these points has some noise. And maybe at some points only, there is high noise, right? So again, this same situation, there may be 5 points in which there is high noise due to some reason. Now, if you take this cost function, these 5 points are going to drive your optimization process. Okay, and even though here 95% of the points seem to do well, because of these 5 points, what the process will do is it will introduce more error in this 95% of points, trying to reduce the error of only these 5% of points. I hope I'm making sense. So I don't want this to happen. I don't want the noise to completely derail my process. Okay, what do I do? Basically, if there is a high error, it should not contribute too much to my cost. That's the basic thing. And how do you do that? Instead of z square, so if you just take absolute of z, you can see this is how it will perform. You take a p which is below 1, right? So if I take a p which is between 0 and 1, there are graphs drawn for different p's. So I think this is for p equals half, if I'm not mistaken. And for p equals 0.1, it's almost flat. So whether the so it's like you would want to select a threshold, right? So of course, higher error should contribute to the cost, but beyond the point, it shouldn't sort of exponentially contribute to the cost. So this is one particular contribution that is there in their paper. Right? They make the cost function just by this change. Instead of square, you take a p which is between 0 and 1. By doing that, you get this sort of a graph, and the behavior is therefore your cost function is insensitive to outliers. So the points where the error is unusually high is what we call outliers. If there are outliers in your process, you use a least square cost function. That's going to derail your process. But instead of least square, if you use a p norm, where p is between 0 and 1, right, you're going to get insensitivity to outliers. But again, this is not easy, because how do you solve this optimization problem? If this is a square, we all can, this is a smooth convex differentiable cost function. So you differentiate this, set it to 0, you obtain the optimal R and T. If p is between 0 to 1, this is not even a norm. Okay, norm has a certain conditions attached to it, 3 of them. I hope some of you at least are familiar with them. And again, whether you like it or not, convexity plays a role. Any norm is a convex function. Okay, but if you look at the other norms here, right? So for example, p equals 1. This is p equals 1 and p equals 2. If you look at the graph of this function, right, you can see that they are basically convex functions, right? But for any p which is less than 1, you can sort of see it sort of curves out this way. Means that this is not a convex function, and norms have to be convex. Okay, cannot. And this is not a norm. Basically, that's what I want to tell you. And the problem is not that this is not a norm. The problem is that this is not a convex function. And if you have paid some attention to my session on day one, non-convex functions are going to again create some sort of a problem. Okay, they are not easy to optimize. So the optimization method they have proposed, I'm not going to go into the details. I just want to give you a summary of this. Is the augmented Lagrangian. Again, I didn't discuss this in the session, but we discussed a more primitive version of this, the dual ascent. Okay, so you've understood the dual ascent, then understanding augmented Lagrangian is not very difficult. Okay, so this is one sort of variant of the basic ICP algorithm. Another framework, right? So this thing is, I wouldn't call it a variant of ICP. It's a completely different framework for finding correspondences. So finding correspondences and alignment is also sometimes called as the registration process. I'm not going to discuss this at all. I'm just giving you the references because I think it's a very nice framework to study. So those of you who are interested, and of course it relies heavily on the two things. Whether you like it or not, linear algebra and optimization. It also makes heavy use of what you studied on Monday, the Laplace Beltrami operator and their eigenbasis. It's just so that you see the relevance of what you have studied in this course.